We have two presentations tonight. One is the Freshman Imaging Project, and the other is the Photoscience Senior Capstone Project. I'm Karen Braun. I'm the Associate Director for the Center for Imaging Science, and myself and Dr. Bob Kremens back there in the corner and Dr. Flip Phillips are the instructors for this course. And we have a great group of students. They'll tell you a little about themselves, but it's a mix of imaging science and motion picture science students. We have a small selection tonight, but we have 17 kids in the class. These are the ones that could be here tonight, and they sort of rotate through who does the presentations and things like that. So
we are the Freshman Imaging Project class of 2024-25, and this presentation is going to be going over the methods for drumhead analysis. Well, I'm Austin Williams.
Yep, I'm Ernst. I'm an imaging science major.
Hi, I'm Astrid Kelly. I'm a motion picture science major.
I'm Maddy, Aldous. I'm a motion picture science major. I'm Sophia, Leonard. I'm imaging science major.
Howdy, I'm Emma Southern. I'm a motion picture science major.
All right. So a quick overview. So a question that we had to answer was, how can we compare calfskin drumheads to synthetic drumheads? And with this question, we had a couple goals that we had to reach. So we had to compare the physical aspects of the materials, we had to compare the timbre, and we also had to see how the environment would affect the materials. And in the end, we came up with an array of solutions, and all of them could fall under these three general categories of physical analysis, audio analysis, and imaging analysis, as you'll see.
So we had multiple materials that we used throughout the project. Probably most important was the parchment samples, which, as you could probably guess, are the main part of the project. We were sent parchment samples from Paul. He's one of the only parchment makers in Britain, and so that's just an example of some of them. They're made from calfskin, and we received about 20 of different parts of the cow. Then that's also a natural drum head, but it came to us damaged. We cut out more samples from it, as you could see. Obviously, another material was the drum heads, and then we also used the drums for analysis, and we used them for audio analysis, specifically with the synthetic drums. And then we built a rim simulator. So with the parchment samples, it was some of the only natural calfskin we had, and obviously it wasn't big enough for an actual drum head. So we wanted to simulate a drum the best we could. So we built the rim simulator to stretch it kind of like a drum, and then we also made the drum bagger for more analysis, and we used a microscope to scan the parchment samples and a light table. For environmental effects, we tested a range of temperatures, specifically in Switzerland, because the project that was proposed to us was from Ernst. He's works for Imperial Drums in Switzerland, and so we wanted to specifically test the factors that would affect drum playing there. So we tested centralized heat at varying temperatures, which showed a pretty big difference. The parchment curled and almost burned. We also tested humidity. We put it in a box with a humidifier at varying humidities, of which the parchment curled pretty dramatically, as you could see. Also wet the sample. We submerged it in room temperature water and ice water. So like if it rained, we wanted to see what happened to the drums if it started raining, if that would have a big effect. It didn't actually have that much of an effect. It obviously wet the sample, but there was no big microscopic difference underneath the microscope. There's a slight visual difference, but not any that would affect it much.
All right, so Sophia briefly mentioned this a second ago, but one of the things we built for this project we refer to as the rim simulator. And what we made it for is the way a typical drum rim for a drum head works is it's this small U-shaped metal rim that has another metal piece go into it to hold the ends of the drum head, which can be tightened on like multiple points around the rim to provide tension to the entire circular diameter of it. So obviously, our parchment samples weren't going to fit in a regular drum rim, so we had to pretty much create our own to fit the rectangular parchment samples. And the way we did that was we were able to use this similarly U-shaped metal channel, saw it in half, and we 3D printed these blocks to perfectly fit in to hold the ends of the parchment. And we put both of those metal channels in a vise that we were able to turn to basically add tension to both sides. And with that, we were able to pretty accurately simulate what a actual drumhead rim would be like.
So for a more physical aspect of our project, we decided that we want to be able to model how actual drum playing would go when used with an actual drum. So because humans do have like inconsistencies and we are not necessarily able to have consistent drumming when using human models, we decided to use a drumming robot. And we decided to build that to be able to model how a possible drum style would go and how that would affect a displacement within the drum head. And what we did was basically make a bunch of things. We utilized accutators to be able to have the drum head like go with consistent force and rhythm. And the way the code works is that it can be modified to fit different drumming styles in order to measure the different ways that the drum can go against the drum like stick. And through that, we can observe the vibrational response of the surface and use that to measure the displacement and see how these play styles are going to affect it. And I'm not sure if you guys saw that earlier, but we had a little clip there of it actually working. So we were able to use that across a few different trials to be able to model a formulaic equation for how the drumming is going to like affect the displacement and the tension within the drum head. And as you can see up there, we have a little graph to give a sort of visualization of that.
You can play that one more time.
Of course.
So all of this comes together to create audio analysis. So the purpose of audio analysis is not only to compare between different heads, so this will include stuff like manufacturing differences, big companies such as Evans, Remo, even the parchment that Imperial Drums uses, but we can also compare the same head. We can compare differences in wear. How might a drum sound different after being played over many years, which is how long some of these animal skin heads last. We can also measure differences in tension, stroke dynamic, many other things. So the items that we're recording and using, what we're recording is the sound of a drum after a single stroke. And these big things that we're measuring are going to be the decay, which is how long the drum rings out after being hit. We remove the attack from the equation, which is when the drum is being hit by the stick, because we don't really want the stick to be part of the equation. Different sticks have different types of tips, which can all affect the sound. We're also looking at how loud the drum is. These can be just from like stroke dynamic, but it can also be differences in the head, how thick it might be. Fundamental frequency, which more or less is just the tuning of the drum, even if drums are considered non-pitched instruments. And then overtones and other frequencies that are unrelated to harmonics. So here is some of the data that we've got between two different heads. Both of them were synthetic alternatives, Remo fiber skins. We had a diplomat and an ambassador model. The difference between these two models is basically the thickness. So the Diplomat is going to be slightly thinner. I believe it's 7.5 millimeters, and the Ambassador is 10 millimeters. So these differences in thickness are going to change things like the decay, the fundamental frequency. So the decay was a bit shorter on the Ambassador due to its thickness. It's obviously going to take a lot more energy to continue ringing out, but also you have differences in tuning, the fundamental frequency. So these two peaks here are the primary tuning of the drum. These differences are about 20 hertz, which can be noticeable to ears that have been tuned to listen to these pitch differences in drums. A lot of professional drummers can typically tune by ear. Some musicians can do that. But consider that drums are not necessarily going to have a specific note. They will have a fundamental frequency that the lugs will be tuned to, that the drum will have a primary sound of, but they're also going to have harmonics and overtones. So these are the other spikes that you see, and they also have a fall off when it comes to volume, which is why I cut this graph off at 2000 hertz, because anything after that is kind of negligible. So these spikes here are going to be a result of harmonics, which are just 2 times the fundamental frequency, but you're also going to have other frequencies that are outside of those harmonics, some which are in the range of 1.6 times the fundamental frequency. And these differences are going to be, well, drums don't sound like anything like a flute or a guitar. That's because they're unpitched instruments. So the reason why a guitar sounds like a specific note is because they have a fundamental frequency and they have harmonics and less overtones that are outside of the fundamental frequency in those harmonics. Drums do not work that way. They work by, well, being ahead, being hit, and having different displacements. They work kind of like waves. When you drop a rock into a pool of water, you're going to have waves that travel out, they come back in through reflection by the rim. A lot of big stuff. But then we also have differences in tension. So these were graphs of different tensions in a single stroke. We have both Remo Fiberskin Ambassadors at 2 different tensions, one at 75 and one at 92. So you have huge differences in the fundamental frequency, 75 and almost a doubling of 199. And if I could play the audio clips, I would, but you can kind of use your imagination about how huge these differences are. And then you'll also see that there are big jumps in between the harmonics that you'll see for the drum tuned to 75 and the one tuned to 92. The reason for these big gaps is mostly just because there's a huge shift between where the fundamental frequency is. There is a bit of a gap before you start seeing overtones and harmonics, usually double, 1.6, 1.4, in those areas. So audio analysis is very important, and we hope to extend it to be able to figure out more things like the age, the tension, because we can guess that many different variables contribute to a sound signature of a drum, like this head being tuned to 92 units and having a fundamental frequency of around 199, and very big gap between in its harmonics and overtones. So I'm going to pass it over to Liam, and he's going to talk about reflectance and transmission.
So in terms of the imaging techniques that we've been exploring, the first one I'll be talking about is using reflectance to calculate the transmission of the drum head. So for this method, we're using a flatbed film scanner with a white background and a black background. And then when you take the image difference between those 2 scans, you're left with a good approximation of the transmission. So then I have a diagram on the next slide, as with the black background, you're only getting the reflected light off of the parchment sample, whereas when you have the white background, you get the reflected light as well as the light that's transmitted through the scan. So then when you take the image difference, you're only left with this transmitted light. So then a similar method that we've used is using a densitometer to measure the optical density of the parchment samples. So then from this, we can get different types of information, such as how uniform the samples are, and then also information about their coloration and then thickness, which are correlated with the perceived quality of the drumhead. Another imaging method that we've been looking at is we've been using a slide with a polymer tape with an aluminum coating. So then when this is pressed against the drumhead, it'll mold to the shape of the surface, but then we know the reflectance properties of the surface. So then if you have two or more images illuminated from different directions, you're able to then reconstruct the local height map of the drumhead. So then we have the test here where we have a red, green, and blue LED. So then we can get all three illumination directions in a single image. And then after separating out by channel, these directions are pretty close to the image, to the gradient of the height map of the drumhead. So this makes the reconstruction easier. So yeah. And then some of the analysis that we've been doing is about getting statistics for if there is a global preferred direction of veins and fibers in the drumhead. One of the hypotheses that we had was if that there would be a difference between synthetic and natural drumheads in both kind of the coherence of the vein patterns and then whether or not there was a preferred global direction. So then in order to get these statistics, we've borrowed techniques from fingerprint analysis to calculate an orientation and then coherence image for the drumhead. So then this is a hue, saturation, value, false color representation of this input image with then the orientation and coherence, where the coherence is the saturation and the orientation is the hue. So you can see in areas where there's very clear veins, you have like very high saturation with a single color, and then that'll change with the direction. And then the key idea of this is that we're able to reduce the dimensionality of the information of whether or not there's a preferred direction, as then from this coherence and orientation image, we can quantize the angles and then sum the coherence values for each angle to create kind of like a wrapped histogram, and then transforming this 2D image into one dimension. And then from that, we can use the mean value to kind of quantify the global coherence-ness of the drumhead, and then the variance is whether or not there's a preferred direction. So then I have a histogram on the next slide. So you can see here that there's a very clear spike from that kind of magenta area, and then other than that, it's roughly evenly distributed. So then, because this is a natural drumhead, you can see that there is a preferred global direction. And then one of the cool things that we've seen is that from the synthetic drumheads, they don't really have a clear preferred direction like this, but their overall coherence is higher. So that's one way that we can differentiate the natural versus synthetic drumheads by this analysis. So yeah.
All right, so those were our methods. The conclusions is we developed all these methods that we just presented to find the differences and similarities between the synthetic drumhead and the calfskin drumhead. And we compared them, we compared timbre with audio analysis, and we do now know how the environment affects materials. So we went through all of these questions, we found all of our goals, and we reached all of them in the end. All right, and our next steps is we have a couple next steps is we need to chain a variety of natural drumheads, good and bad for comparison, because we didn't really have that many like materials to go off of. We only had a couple little sheets of the drumheads. We need to combine various of the project components into like a complete imaging system, because there were a lot of things going on, and better organization for more of like a overall thing would help a lot. And we also need to create a system of comprehensive analysis of what makes a good drumhead. All right. And here are the acknowledgements. The names up there with the RIT, or the help here at RIT. Paul Wright, he supplied us with a lot of the parchment sheets, and Ernst was, he was the reason behind the question in the first place. All right, and any questions?
Well, I have a lot of questions, but first of all, did you get to go to Switzerland to get the drumhead? Oh, shucks.
That'd be cool.
No,
It's almost the same.
I think Switzerland has Home Depots. They could have just gone to the one there. No, great job. Could you go back to slide 5?
Slide.
Yeah, absolutely. That's one of the first things I always tell my students. I was interested in that upper left-hand corner graph. Can you talk a little bit more about what's being measured there and how you did that?
Oh, it's mainly measuring luminosity versus wavelength. Basically, it's how the drum heads change during the tests, and like how much light capacity would act before and after the tests.
So can you describe a little bit more about the instrument setup? I mean, what was illuminating it? And I assume that the vertical axis is kind of just a relative quantity. It's not a physical quantity in any way.
Yeah.
Is it? This was from a paper. So there could have been a little citation at the bottom saying where you got it from. That would have helped. Okay. Slide 8.
Oh, God, can I continue with 5 for a second?
Sure. Yeah.
Switzerland weather can reach highs of 80 to 90 C.
Oh, no.
I don't think it can do that quite yet. Is that F?
Yes, it's Fahrenheit.
Okay.
We tested it with the heat gun in Celsius, and we made a small error on the slide.
I was giving them the benefit of the doubt. Maybe they work in hot boxes.
Yeah,
right. Okay, slide 8. So maybe the answer to this is it came from a paper, but the equation here that's shown, is this something you developed? What are the vertical axis units, or is this just for illustrative purposes?
So the main equation is something that we developed as a sort of general equation to measure the displacement and tension within the drumhead. In terms of the axes, the left or the x-axis should represent like the amount of times that the drum was hit, and then the y-axis just refers to like a general quantification of the displacement. It should be in about micrometers, I think.
So it's a distance? And
Well, I
the
mean, yes.
horizontal axis is...
There's like a set amount that there's like a set amount of tension that the drum has before it's even used. And then every time that it's used, it loses a bit of its original tension, which corresponds to sort of growing thinner and sort of expanding in on itself due to the depression formed by using it for a while.
So how did you measure the displacement?
So the displacement, this was a little bit more of a guesstimate, I guess. But we mainly just measured the displacement by just seeing the tension within that and then using a few equations using like cosine theta to make it into a displacement.
Sorry. Thinking about that in your photograph of your setup, I don't remember seeing any strain gauges, or how were you measuring the tension?
Well, we measured a few like test trials, but it's not like necessarily a full-on quantification of it or set quantification of it. So this is again more of an estimate.
Okay, thanks.
I had another one on that same equation. I mean, the thing that struck me was the fact it's a cosine. Because I would have thought it would have been a sine. My reason for saying that is when t equals 0, I would think that's just as the thing's being hit. So there's no displacement at t equals 0. Then you hit it, and then it displaces. So I would have thought at t equals 0, it would have been 0, and then it would have oscillated after it got hit. So, it's kind of I don't know, a mundane question, but should that be a cosine or a sine?
If you're cutting off the attack and it's starting the moment the drumstick is no longer a factor in the vibration, then I guess it would start at max displacement. So
I think a lot of these questions are that it's really unclear to the audience what the quantities are here. For example, the horizontal axis. At one point, I thought you said it's the number of times that the drumhead was hit, or is it time like in milliseconds? What is the horizontal axis here?
So the horizontal axis would probably be the number of times that was hit. It's just, it has the like numbers just as a, like, that's just how it's graphed within Mathematica. But yeah.
So when you say the number of times it was hit, this is looking at the wear of it? Like if you hit it lots of times, the maximum displacement is less?
A new peak, right? You'd have a decay, and then hit again would be peak would get smaller and peak smaller, right?
Pretty much, yeah.
But that just has one decay. Right.
So it's mainly just, again, this is more of an estimate, but it's mainly because of how it affects it over time and how like it affects mainly the playing style. So it kind of ties in with what Emma is sort of doing with how it mainly affects how it sounds. So this is more sort of for that, I think.
Could you just say, you say over time, what interval of time? Like seconds, years, days?
So probably not years, but it would probably around seconds or minutes, depending on how long the drum is being played for. And that's mainly what the robot was for, is to measure it over, like, say, doing it for a few seconds versus doing it for a few hours. And it just provides versatility when it comes to that.
So it sounds like the vertical axis is a maximum displacement as a function of when it was hit, not as Roger seemed to interpret it. This is the plot of the displacement. Yeah, the oscillation, but that's doesn't seem what you're saying it is. Is that true?
Well, I mean, it's not necessarily the oscillation, because the oscillation would mainly be used for the like tension that the other people have done. But this is, I guess, more of a like corroboration of.
So it looks like what you're saying is the general equation with the dampening of a single hit over time, but the units are somewhat arbitrary. Because I see, you have 8x there. 8's a nice round number, and probably the frequency of a real hit would be something more, not so round. And I'm also guessing that 16 is probably not 16 seconds, because that would be a hell of a long time for a drum to ring out. And 16 milliseconds seems a bit short. So I think what one of my friends here are getting in on is, you call it friend.
My apologies.
He sat through my class.
My apologies. I think the point is that graph would help the viewer if it had a little more annotation around it and then described what I had, and also had some numbers which may be more consistent with what you'd expect from a real drumhead.
Yeah,
If that's what it is.
Wayne's exactly right. My interpretation was that was the impulse.
Did you have, I know you had some actual images of the strikes and I think you took them out, but it looked similar, but that was the actual measurement.
So
Is it sort of saved on a hidden slide or anything, or is it gone?
no, I did remove that.
Okay, but can
That's
you
my,
talk to- No,
that's,
that's okay, but can you just talk to what you actually measured in terms of,
Yes, in terms of actually what the decay looks like, I put up the graphs of frequency response, but the decays from the drum did actually have this sort of fall off. So at 16, I would say that's around 1.6 seconds in my area. That's when the drum is effectively no longer ringing out. It's at 0. So at least the way that I saw it, the vertical axis was volume. Now, digital programs don't measure volume in the way that we hear it. It measures it from 0 to -99, which there is a way to change that, and I will need to do that in the future. But the fall off that you see is more or less similar to what you'd see from a single stroke from the moment you hit it to where it's no longer ringing out. I hope that clears up some questions.
If I can, two questions. Hopefully I remember both of them. At the very end, you said, the goal here was to look at for an optimal drum surface, and you have the synthetic and you have the real membrane, the real skins. I'm a little, drums coming off. You can go to a drum store and you can spend as much money as you want to buy as much different ones.
Right.
Help me out what you mean by the ideal, and what is the comparison that you're comparing the two? Was it to make the skins seem like the synthetic seem like the skins, or to seem like a third thing, which is an ideal?
So in terms of the drums that we have, the synthetic alternatives like the Remo fiber skin, my understanding is that their advertisement is it's supposed to simulate from a drummer's perspective, the feel, the sound that you would get out of an animal skin drum head. So that's on their end, what kind of factors they're contributing into. I'm sure some of that is also in visual, since the fiber skin models that we have do have some similar, I guess, veining structures that Liam saw.
So the natural head is the gold standard, and the question is, how well can you get the synthetic to sound and feel and be like?
Yes.
Okay, and the last question I have is, you showed the plots of, you talked about the frequency decay. So if I imagine a drum being hit in my head, that doesn't sound right. If I imagine in my head the sound of a drum being hit, the initial attack is going to be rather sharp, and then, as you mentioned, there's a dampening effect which occurs, which is going to mean that it's not a time invariant frequency response. Right. The initial hit's going to have more high frequency energy, and then the over time is going to be a low frequency. Yes. And you plotted this over the entire 1.6 seconds.
Yes.
It seems like convoluting it's conflating two separate things.
Yes, it would have been smarter to have it over shorter durations of time on maybe the order of milliseconds. So the decay closer to the attack would likely have
like an initial hit, kind of frequency response, and a mid or late hit.
Yes.
By the way, despite all these, it was a wonderful presentation, and it was well done.
Despite.
Very good.
Ask about how you computed the frequency content, but it sounds like there are many ways to compute the frequency response, and a short time Fourier transform would have been an alternative to maybe separate it out.
From my understanding, the Audacity, the digital audio workstation that I was using for recording, has a built-in plot spectrum, which just plots out the frequency response. This is not a graph of what it gave me. I exported the data points that it gave me and put it into an Excel sheet and ended up with this because it was a lot prettier to look at, in my opinion, at least, and also a lot easier to manage.
What did the Excel?
So Audacity, I believe it was doing an FFT.
Yeah.
Yes.
But our spreadsheet's just.
I exported raw data points from what Audacity gave me into an Excel spreadsheet just so I could have a cutoff at like 2,000.
Okay.
Yes.
Yeah, because the Audacity does do rolls off.
Yes.
And you can pick your Hamming window, your windowing functions and all the other goodies. Very good. Well, thank you very much.
Thank you.
Okay.